Hello, everyone. What I want to do is do a quick review of Kernel Ridge Regression and in particular discuss how to speed this up incredibly so that it's largely practically useful when you have a decent amount of data. I don't know exactly what the rule of thumbs are, but yeah, in particular, I'm going to discuss random Fourier features. Really a beautiful connection between kernel ridge regression, positive definite functions, and Fourier inversion, more generally Bachner's theorem. But I would say practically it's essentially Fourier inversion. Yeah, I'll go through basically a good chunk of this paper. Try to make this paper make sense. Um, Yeah, this won the NeurIPS Test of Time Award 2017. So it's a pretty big deal. Definitely a lot of research going into this. So this itself is from 2007. So with respect to kind of this course, this is definitely the most modern thing we're doing. And ironically, it's not very deep mathematically. It's essentially Fourier inversion, Monte Carlo approximation. Yeah, there's not a whole lot more mathematically than that. Um, but anyway, and yeah, so I will not assume that you've seen anything from linear regression. I'll go through kind of I'll discuss. It's not very deep. It's very quick, but I'll discuss very briefly why, when you have linear regression, you can often go much faster than more general kernel ridge regression. So anyway, let me just get to it. Right. So yeah, quick review of kernel ridge regression. The work is plugged in. Oh, sorry about that. Okay, so remember, the idea here is, and I'm not going to go through all the details, or I'm not going to go through any of the details. Um, so let's say we have, basically, yeah, let's say we have a set X. In practice, this will be a subset of Rn, but it could be Cn. Yeah, for practical purposes, it's Rn. And let's say we have data and input output data equals 1. That's a subset of X times, in general, C. In practice, it will be R. So, right, this could be, YJ could be the height of a person. It could be spam, no spam. It could be a million different things. XJ is just kind of the data that we're given. Right. And the goal, just general regression goal, is just to find a function fitting the data. So find function x to c, where right, this is true maybe I'll do X. I guess I'll stick with J. And we don't want this for just our training data, but we want this for all kind of inputs and outputs, for all future data that we're given, inputs, outputs. Right. And so we don't want that's too much to ask, but we want this to be roughly true. Standard regression. Yeah, we want this to be true for all current. If it's true for all current, but it's miserably bad for all future data, then that's just a classical fitting. It doesn't help us. Okay, and one way to do this is, well, kernel ridge regression. In particular, you want to, we need a nonlinear, if you want to, if there's a nonlinear relationship between xj and yj, and you don't have a lot of data points, this is a good method, a classical method to do. All right, so let's say H, let's say it's the reproducing kernel Hilbert space. And so what are we going to do? We use H for regression purposes, so we want to solve the following problem. Find a minimizer among these functions as follows. Just least squares, basically, among my input outputs. And we want a penalty that not only prevents overfitting, but as seen, allows us to invert even when the kernel is not necessarily strictly positive definite, which in practice it might not be. For particularly linear kernels, you don't necessarily get strict positive definiteness unless the vectors are linearly independent. All right, and the theorem. Finite representer theorem is as follows. So let's call this star here. Any minimizer to this here is of the form right, it's of the form f of x, just a finite linear combination of your reproducing. So let's say k of x, y is my reproducing kernel. Plop in your inputs here. All right. Okay, so that means what we need to solve is basically the same thing as this. This is not standard notation, but if anything, call it Vn. But the same thing, but just restricted to these kinds of functions. So Vn is just going to be finite span of these kernel functions on your input, given input data points, the n input data points you have. Otherwise thing. I forgot to mention, but lambda will be positive. Right, squared here. I did good. Solve this. Right. Again, this is just span of these J functions. All right, so let's call this whole thing here. I guess I'll just spell star. All right, and just literally plugging in. I did this before, but it's a good exercise to do it. Here, let me do this just like before. Let me actually call this thing here star star. Right. So we plugged in and so we said, let's say alpha is this vector here, alpha 1. Yeah. Let's say k. So this is a n vector. Let's say k, big K here is my n by n matrix. I, X, J. Yeah, so right. Then what do we have? Yeah, just literally plug in, easy exercise. This is going to be equal to second. Yeah, so it's going to be equal to of course, let's say y1 commas instead of y's, but same thing. X is just my x vectors. For x is my n tuple. Right, so this is going to be y minus k alpha. Don't need x here. Don't really need the x vector. And it's just obviously matrix multiplication. In particular, this here is going to be the sum. And this here is going to be alpha. Okay. So yeah, remember we now have a new problem then. Have the third step. Find Ardman. So these could be technically in CN. In practice, you want to restrict to RN. So I'll just be practical and restrict to RN. Right. Find alpha to minimize this. Arrows here. This. Yeah, and something to keep in the back of your mind is that this here is always going to be bigger or equal to 0 because it's equal to lambda, the norm of f, squared if f um, is of this form. That's something to keep in the back of your mind. Look at that in a minute. And technically, these are both. I guess if K is complex, we technically solve this. But again, in practice, everything's going to be real. Technically, we're going to allow this. This would be big N. All right, well, you can literally take gradients and just check that the solution here is simply uh, kind of like with linear regression. It's K plus lambda I n times n. I is the identity. Inverse. Okay, so yeah, this is great in some ways. One thing to keep in the back of your mind is that we really didn't, we have high dimensional data that's not really reflected here. If you have only a small number of data points, but it's high dimensional, you're still only inverting a small matrix n by n. On the other hand, if n is big, that's bad because you're inverting n by n matrix. So n is huge, big N is huge, then yeah, we have problems here. Okay, yeah, so we want to talk about how to fix this. And one thing to kind of emphasize whenever this is taught, um, we use nothing of the Hilbert space. So in practice, you don't care what H is, and often you really practically don't know what H is. I mean, in theory, it's in theory, H is just going to be the completion of the span of reproducing kernels, but or the closure of the span? What does that look like? And in practice, a lot of times you don't know what it looks like. Um, when you do want to kind of theoretically look at kernel ridge regression, so for example, if you want like Rademacher, Gaussian, whatever complexity bounds, then you do, and researchers often are interested in what the Hilbert space is, but practically you don't care. Right. So Yeah, so that leads to the very practical question. So let me actually write some examples down for, yeah, so let me do something. So that leads to the following very practical question. So given, K, given basically a function of two variables, that's either real or complex valued on X times X. When does, there exist a reproducing kernel Hilbert space H, um, with reproducing kernel of X. And the answer is, well, okay, you have, if two things are true. So one thing, I'll erase this in a second. One thing to notice, that let's suppose that K does come from a reproducing kernel Hilbert space. One thing to notice is that if we're dealing with, if K is complex valued, then this is going to be not quite symmetric, but stick a complex conjugate and it'll be symmetric. So what do I mean? Just use the reproducing property. So this is going to be, I'm looking at this function here with y fixed. And I'm hitting it with the x reproducing kernel. That's the basic property of reproducing kernel. So do something just trivial, just bring, just switch the order here, get a complex conjugate. So if K is real valued, then it'll be symmetric. Right. And so now it's the same thing, but this is complex conjugate K of Y. So that's the first thing we need. Okay, X, Y is complex conjugate K of YX. This is for all X and Y in big X times big X. Two, as I mentioned, for any N, big N, this here is equal to norm squared of F squared, where F is just the following. Yeah. So in particular, we don't really care. All we care about is that this is non-negative. This is bigger or equal to 0. So in other words, I mean, I don't care about this. This is always not negative because the norm squared of something. So in particular, right, what's important is that this, if K comes from a reproducing kernel Hilbert space, or rather if K of XY is a reproducing kernel of a reproducing kernel Hilbert space, then this is always bigger or equal to 0 for any input xi, xj, for any number of input points, big N. Okay. So that's the second thing we need. And Yeah, this is called the Moore-Aron-Sagen theorem. I'm probably pronouncing that incorrectly. Um, but so for any and natural numbers, any vector alpha, generally in Cn, and for any let's just I'll do right. So for any x, right, like this, just for any n, any vector n, any tuple x, the following is non-negative. So in linear algebra terms, this is just saying the matrix K, remember what big K is. Big K is this right here. Just take your inputs, xi, xj, form this matrix. This matrix is positive. In pure math language, we say this is positive semi-definite, and it's positive definite if we have bigger than zero whenever alpha is not zero. And it's a little confusing in data science terminology or data science parlay. It's positive definite. Um, but yeah, you do not need actually that this is strictly positive when alpha is not equal to zero. Okay, right. So what I'm going to do in the next video is a really nice connection between when K is positive definite and the Fourier transform. Now let me just do some examples. And right, like I said, this is called the Moore-Aron-Sagen. Um, I'm not with well, whatever. I it's SJ, AN maybe. Yeah, and the proof is a bit anticlimactic. It's not a terribly deep theorem. Mathematically, all you do, as I said, basically take the completion of um, finite linear combinations of reproducing kernels on your uh, on X, basically. Um, the set X. That's that. Um, yeah, really not much more to it than that. And then just check that this Hilbert space works. It does. Okay. Right. So just some examples here. Uh, so the simplest example is just, and a very important example. So here, big X is just going to be Euclidean space. Um, so let's just say, I mean, more generally, it could be Cn, but yeah, say big N is reserved for the number of data points. So this is called the linear kernel, and we'll see why this is extremely useful in real life versus um, uh, more general kernels. So the second example we've seen is comes from the reproducing kernel Hilbert space of band limited functions whose an L1 continuous on the real line, and the Fourier transform vanishes away from minus b to b. This has reproducing kernel 2 pi b x minus y over I y. Yeah, I don't know what the Hilbert space for 1 and 3 are. Three I know, so let me just do 3. I'll remind you what the Hilbert space is for 2. Um, this here, the Hilbert space is actually a bit complicated. You need complex analysis to describe it. And here, this is just like a parameter. It's like it's like a parameter to tune. This last one's called the Gaussian kernel. This is probably the most famous one because you can basically capture a lot of practical nonlinear regression. Or you can solve a lot of practical nonlinear regression problems with picking the right parameter gamma bigger than 0. Parameter. And right, remember this is F L2 of R, F continuous on R, and F hat 0. For almost every omega n, sorry, not n minus b. Yeah, remember we all these kind of functions, we have a sampling theorem for that. That's called the Paley-Wiener series. So yeah, 3 very common examples. There's a lot of others. The Matern kernel is a little complicated, but it's a very practical kernel. A little surprisingly, you don't see 2 used in concrete regression problems. I'm not sure why, but yeah, you don't. I would figure you'd see this in signal processing, but you just. All right, so I'll do random Fourier features in the next video. So take care. So long. Take care.